All right, squad. This will be the final section of our vector calculus endeavor for now, and it's talking about the divergence theorem. Now, it's helpful to have a side-by-side of Green's theorem and the divergence theorem. This is Green's theorem in flux form, and we'll go over it in more detail. But then on the left side we have the Green's theorem, and then on the right side we have the divergence theorem. It's because these notes, they tell a story. Now, on the left side with Green's theorem, it shows how to connect a two-dimensional boundary curve to the flat area closed inside of it. And on the right, we have the divergence theorem, which scales that exact same concept up into three-dimensional space. So we're connecting the solid's outer surface to its entire inner volume. And together, the story that's told is one of beauty and symmetry. You can measure what's happening inside of a region either by looking at its outer boundary or by adding up all of the sources within the interior. So here's the core patterns. I have the textbook definition for the divergence theorem down below. Um, but let's try and look at the core pattern here before we get into that, because it's a little bit much. The core pattern is both theorems share the exact same mathematical philosophy. They bridge the gap between an outside boundary and an inside in the inside space. Green's theorem is in two dimensions, and perhaps I should specify that this is in R2, two-dimensional space, and the divergence theorem is in three-dimensional space, that is R3. So Green's theorem, it's two-dimensional. It translates what happens around a flat perimeter C into what happens across the two-dimensional area R and sitting inside of it. The divergence theorem in three-dimensional space it does the exact same thing, but in three-dimensional space. It upgrades the parameter to a 3D shell, which is denoted with an S, and the flat area to the solid volume, which is denoted with a D. Okay. So the textbook definition, this is from Calculus by Briggs. It says let vector f be a vector field whose components have continuous first partial derivatives in a connected and simply connected region D in R3 enclosed by an oriented surface S. Then the double integral S of vector R dot vector n, its normal vector, integration with respect to the arc length equals the triple integral of the divergence of f dv, where vector n is the outward unit vector normal to S. So again, that's the double integral for S of vector f dot vector n, integration with respect to the arc length, equals the triple integral of the divergence of vector f dv, where vector n is the outward unit vector normal to S. Now, the divergence theorem, it states that the total net flux of a vector field flowing outward through a closed 3D surface is equal to the cumulative sum of all the sources and sinks operating within the solid volume inside of it. So in short, it lets you calculate what's happening across the boundary, either by looking directly at the outer shell or by adding up everything occurring throughout the interior space. And in two-dimensional space, if you remember, a source in R2, well, that's going to be when you have your two-dimensional space, right? And then you have the arrows are flowing outwards. We talked about that a bit. Right? The arrows are flowing away from the origin or whatever space, whatever point. It doesn't have to be at the origin. And then a source in R3, it's the same sort of idea, right? Like I could try to do this in three dimensions. For a source in R3, we'll do it in the eighth octant, and we'll see that all of these vectors are pointing away of one specific spot, acting like a source that's creating motion, right? Or you could even think about it as like if it's the sun, right? The sun has a source of light, and the light is emanating from the sun, away from the sun, and the sun is the source, right? You could think about it like that. And then this is in R3. So that's in the third dimension. And then if you think about like a sink in the second dimension, right? It's exactly what it sounds like. The arrows are going towards a specific spot. They're all pointing in a specific direction. They're all pointing to something. Or if you think about a source, or excuse me, if you think about a sink in the second, and excuse me, if you think about a sink in the third dimension, well, that's the inverse is true, right? So like it's a spot where all the vectors are pointing into one, all the motion is going into one spot. There's force. These vectors are going, they're sinking into one spot. Think about like a drain, right? The drain, this is pointing towards where the water drains out. Okay? Um, there's something else I wanted to mention. Uh, there's a couple other things that I actually wanted to mention. But we'll start with the breakdown of each of these equations thoroughly. I think that's a good idea. Let's look at this first expression. Let's make sure that we really have an understanding on what's going on here before we work through a couple of problems because it's important. You see this new integral, and instead of having bounds of integration, there's just a c on the bottom. You got vectors, and they're taking the dot product, and then you have ds, and you don't even see any variables that have an s in it in the integrand, except for the ds itself, and it's sort of confusing. Um, so what this is, this expression, it represents a line integral over a closed curve, and that curve is c, right? You can see that there's a c right here, and there's a c right here. It's calculating the total outward flux of a vector field, vector f, across that boundary curve by taking the dot product of the field with the outward unit normal vector, vector n, with respect to the arc length, which is ds. Mind you, this takes place in the second dimension. So again, in 2D space, flux measures how much a vector field passes through a closed curve. Um, my question was like, outward flux versus inward flux in 2D space. It's sort of easier to visualize flux in 3D space for me because if you have a box and the arrows are going inwards, um, that opposes the normal vector, and thus it's going to be a negative. It's going to be negative flux, and if it goes outward, that goes with the normal vector, and that it's going to be positive flux. And like that's sort of easier for me to conceptualize, right? If you think about like a three-dimensional box, when you think about a flat space, in R2, right, like that or like that, it's like we know the outward flux measures field lines that are exiting an enclosed region. So the direction in the vector field, it points in the same direction as the outward pointing normal vector n, and of course the normal vector n is always going to be at a 90-degree angle with the curve. So um, it indicates a net source inside of the region generating the field, and then an inward flux is measuring the fluid or the field lines, right, entering an enclosed region, um, or I guess a specific region. So the vector field points in the opposite to the outward pointing normal vector, vector n. And these mathematical attributes are extremely interesting because when you think about it in two space, it's like if it's in two space, the whole thing is flat. So how do you know if the how do you know if the flux is negative or positive, or where the arrows are pointing graphically speaking? And it's like, well, even if the surface is flat, any closed curve, like a circle or a square, that's like shown the region that's enclosed, right? So there's a curve that's closed. It naturally splits the 2D plane into two distinctive zones. What's outside of the curve and what's inside of the curve. Um, and uh, and so we have to, establish the boundary rule, and then well, the normal vector n, it's a line that's perpendicular to the curve, and it's always pointing away from the interior region from the interior from the curve. So like, so it's always pointing up. So like if your curve is moving counterclockwise, which in this case it is, um we can find the outward vector, or we can find vector n at any point x and y by taking the curve's tangent vector and rotating it 90 degrees clockwise. We can use the dot product test to see if the vector field f is pushing fluid out or pulling it in at specific points on the boundary if you calculate the dot product f dot vector n, which is what's going on in the integrand. Um, so so yeah, so if the vectors are going inwards, that's opposing the 90-degree angle to any point on this curve, right? So if they're going inwards towards in the region, that's actually negative. If it's going outwards with the normal tangent vector, vector n, then it's going outwards. So little confusing, but hopefully that cleared things up. I mean, it did for me at least, right? Um, and so, and this is just, yeah. And so anyway, so that's like the first part of the equation. Then we look at the second part of the equation, and now it's like, okay, div, like what is that? Why is there double integral? How does this equate to it? Like what's even going on? Well, this expression represents a double integral over a region R, and that's calculating the total net accumulation or total divergence of a vector field, vector f, within that two-dimensional area by integrating the divergence of a function with respect to the area element, which is denoted as dA. R is the region, C is the curve, and dA is the area element. Now moving on to the left side of the divergence theorem equation, again, it's a lot going on. It's different, right? Like this is not the same. These two, 1 and 2, they're not the same. So let's just try to break this down. Well, first thing to note that this is in 3 space. This expression represents a surface integral over a surface f. Remember that a surface integral covers the total closed boundary surface enclosing a 3-dimensional volume, like an outer shell of a 3D shape, like a cube or a sphere or a cylinder, whatever you'd like. So in this specific expression here, we're calculating the total net flux of a vector field, vector f passing through that 3-dimensional surface by integrating the dot product of the field with the normal vector n with respect to the surface area, which is ds. So so maybe I should have left these here, like if it's going like the vectors are going in, whatever, right? But now we're looking at this, and we're taking this logic, we're expanding upon it in such a way where it's like, okay, like if I have a cube, right? And we went over this a little bit before, but it's nice to have a refresher, especially when we're doing like a side by side with these equations, because you know how this stuff goes, right? It's always good to have a visual. Um, and we can even get some colors in here, we could utilize our resources. So here's the normal vector. Here's the normal vector, right? We were looking at this point, right? So this is the normal vector. And the normal vector goes up at a 90-degree angle towards this surface that we're looking at, right? And well, if we have vectors that are going inside of this box, right? Vectors that are going inside of the box, that opposes the normal vector. That opposes this. It's going against it. And due to that, it's going to have a negative flux. So that's what that means. If there's motion vectors that are coming from the box, that's going with the normal vector. So that means that it's going to be positive. So just remember, right, like that it calculates the total net flux. And if the net flux is negative, the arrows go inward because they oppose the normal unit vector, and if the flux is positive, the arrows go outward because they flow with the normal unit vector. This doesn't have to be a cube. It could be a cylinder. It could be a sphere. It could be whatever you want. It just has to be a 3D enclosed surface in this context. Now let's look at this thing. Which we're showing that these are equal to each other, but it's just like now there's like there's 3 of them. Like what's going on? And well, this expression represents a triple integral over a three-dimensional solid region, D. And it's calculating the total cumulative divergence of a vector field, vector f, throughout that volume by integrating the divergence function with respect to the volume element, which is dv. In this context, divergence measures the net rate at which a vector field spreads out or originates from a specific point in space, acting like a density of sources, a positive divergence for sources or negative divergence for sinks. Divergence tells you how much a vector field is actively expanding or emerging away from a single point, behaving like a source or a sink. And so C, right? We went over this. C is the curve, it's a closed curve, right? R stands for the two-dimensional flat region enclosed by the boundary curve, C. D stands for the three-dimensional solid region enclosed by the boundary surface S, and S stands for the closed two-dimensional surface that forms the outer boundary of the 3D volume C, S. All the divergence theorem is saying is that the total net flux of a vector field flowing outward through a closed 3D surface is equal to the cumulative sum of all of the sources and sinks operating within the solid volume inside of it. In short, it's letting us calculate what's happening across the boundary, either by looking directly at the outer shell or by adding up everything occurring throughout the entirety of the interior space. Everything that's occurring, to be specific, we're talking about sources and sinks. And so that's what's going on with the divergence theorem. Let's work through an example, shall we? This question says, verify both integrals in the divergence theorem for vector f equaling x, 2x, y, 3y, and z, 4z. D equals x, y, and z, x squared plus y squared plus z squared is less than or equal to 4. Well, when we look at this, we should look at this equation here and be like, all right, like D is well, it stands for like domain, but really what it is it's the region that we're looking at. And when we look at this equation, we can see that this is a sphere with radius radius 2, right? Yes, radius 2. This is a sphere. We can see that this is a sphere of radius 2. In fact, because it's actually uh, less than or equal to, it's a ball. So let's try to draw that out in 3 space. All right, so this is a ball in 3 space. And moreover, it's a ball that has a radius of 2. 2, 2. All right, so that's my region D. It's a 3D ball with a radius of 2. So I'm going to start calculating my surface integral, which is why I have this here. This is what's going to help me calculate my surface integral. Now, I'm using the divergence theorem. It's asking me specifically, verify both integrals in the divergence theorem for this specific vector. And so that's why I have the surface integral formula here. So z is not explicitly solved for, so I need to parameterize this. This is a sphere, so I am going to parameterize it using our chart. This is a sphere, so we're going to have to parameterize it, and this is how we're going to parameterize it right here. We're looking for vector r of t. And, well, we know that it's a radius of 2, so when we look at our chart, A is going to serve as the radius, so we're going to have 2 times cosine, excuse me, we're going to have 2 times sine of u times cosine of v in the x component. We're going to have 2 times sine, no, so we're going to have 2 times sine of u times sine of v in the y component, and we're going to have 2 times cosine of u in the z component. Now I'm going to take the derivative of vector r of t with respect to u in order to find our t vector t, our tangent vector, the t vector t of u. How am I going to try to do this? Let's see. if this is F, this is G, and this is H, then I'm gonna do it like this. This is gonna be 2 times cosine of U times cosine of V for the first for the F component or the X component. Um, for this here, I need to take the derivative of this thing with respect to U. So it's gonna be 2 cosine of U times sine of V. And then for this thing, it's cosine of U, right? Yeah. 2 times cosine of U, which is gonna be negative 2 times sine of V. No, negative 2 sine of U. Vector T sub V. So we want the partial of F with respect to V. We want the partial of G with respect to V. We want the partial of H with respect to V as well. And so we have to go in on taking these derivatives, and that's going to be like, well, the partial of sine, the partial derivative of 2 times sine of U times cosine of V with respect to V. I think that's going to be negative 2 sine squared. No, just kidding, that can't be sine squared. How could it be? Negative 2 times sine of U times sine of V. I think that's the answer to that one. And then as for the partial derivative of 2 times sine of U times sine of V with respect to V, well, I think that's actually going to be 2 times sine of U times cosine of V. Pretty sure. And when we take the partial derivative of 2 times cosine of U with respect to V, that's just going to be 0. We need to find, like, what is vector T sub U cross vector T sub V. So we'll start out with our I hat, and 2 cosine of U, it's going to be 2 cosine of U times cosine of V. And well, for j hat, it's going to be 2 times cosine of U times sine of V. And then we'll do our k hat. That is negative 2 sine of U. So that's going to be vector T sub U. So for vector T sub V, it's going to be, for the I hat, negative 2 times sine of U times sine of V. Now we're going to do our j hat. And for our j hat, it's going to be 2 times sine of U times cosine of V. And then for our k hat, it's just going to be 0. And so let's just write out the template. Something minus something I hat minus something quantity j hat plus something minus something quantity k hat. Let's start by evaluating the cross product. We'll begin with I hat. So I'm going to cross the way down, and I'm going to cross the way to the side. And that's going to be 2 times cosine of U times sine of V times 0. Well, that's going to be 0. From that, I shall subtract negative 2 times sine of u times 2 times sine of u times cosine of v. Oh, that's going to turn into plus what? 4 sine squared of u times cosine of v, I think. That's going to do it for our I hat. And then we'll move on to our j hat. I'll be left taking the determinant of this matrix-like thing. It's got a similar mechanics to matrix C, but we're going to do 2 times cosine of u times cosine of v times 0. It's going to be 0. And then from that, we're going to subtract what we get when we do negative 2 times sine of u times negative 2 times sine of u times sine of v. That is going to be a positive 4 sine squared of u times sine of v. So that will be our j hat. Well, what's going on with k hat? Yeah, we have to find out. It's up to us. K hat is going to be 2 times cosine of u times cosine of v times 2 times sine of u times sine of v. What is that? 4. So who's doubling up? The cosines are. So we're going to do sine of 4 times sine of u times cosine of u. And we're going to try to be conservative with space because, well, we got more to write. So this is going to be cosine squared of v. From this, we shall subtract what we get when we do 2 times cosine of u times sine of v times negative 2 times sine of u times sine of v. You know, this is going to be plus 4. Yeah, plus 4. Who's doubling up? Sine squared of v. So it's going to be sine of u cosine of u sine squared of v. And then that will be our k hat. So let me just check my work. The only thing is, it's like when I see the sine, I see a sine squared of v, I see a cosine squared of v. Like, I think that's going to be a Pythagorean identity. What are we going to do? That becomes a positive. So I'm going to say that for the x coordinate, because I'm going right into vector form. I'm putting this right into vector form. We're going from the I hat, j hat, k hat business right to the vector form. I just want the vector coordinates. Maybe I should remind you guys 6 times that I want the vector coordinates. Alright, so what's going on with the j hat? Negative 4 sine squared of u sine of v. We're gonna have to do some manipulation. Actually, there's a sine of u and a sine. Actually, there's a 4 sine of u and a 4 sine. There's a 4 sine of u and a 4 cosine of u attached to both of these. So if we just factor this 4 sine of u times cosine of u out of both, we can be left with a Pythagorean identity. So I'm just going to take it out. I'm taking out the 4 sine of u and the 4 cosine of u. I'm going to just snag those right out of there. And, well, we're going to have sine, well, let's do it in order. Cosine squared of u plus sine squared of u. We're going to grab that Pythagorean identity and try to just make this a little bit more compact. Just sort of collapse it a bit more. That's going to be a 1 right there. And, well, I'm going to have to grab this thing. Say hi to my YouTube channel. She broke my concentration, but it's okay. We're gonna keep the ball rolling. Um, where were we? What were we doing? No. Let's see here. Oh yeah, we were to apply the Pythagorean identity. So we've identified that this is going to be a Pythagorean identity, which basically means that it's just going to turn into one. Um, with that, we can sort of collapse this into the z coordinate into a smaller expression. That is what we're gonna have for x sine squared of u cosine of v. For y, it's gonna be -4 sine squared of u times sine of v. And then yeah, and so this is just gonna be this is just for the z coordinate. This is just gonna be sine 4 sine of u times cosine of u times 1, which we're just gonna leave that as is, um, because it gets smaller, you know. And well, now well, the divergence theorem, it says that we need to um, well, we need to dot them. We need to dot them together. So we dot them together. We could do it like this. Let's see. I'll write out the formula of what we're doing. All right. And so now it's like basically what we need to do is we need to take vector f, which we're given the vector coordinates for that, and we're gonna dot it with the cross product that we've just generated, or I guess recovered from the tangent vectors, the cross product of the tangent vectors, which was the I hat, j hat, k hat stuff. And so, you know, when we recall the parameterization that we did previously, yes, right here. Um, it's well, for x it's 2 sine of u times cosine of v. For y it's 2 times sine of u times sine of v. And for z it's 2 times cosine of u. And that's shown right here. So I'm just gonna grab that. I'm just gonna do this. Um, but instead of well, instead of f, g, and h, I'm gonna say that this is now, I mean, not that it really matters, but this is gonna be x, y, and z. And the reason for that is because when I grab the vector given to us, that is vector f equaling x 2x, y 3y, and z 4z, um now we can Now we can change our vector f before we dot it, if that makes sense. And if it doesn't, that's fine, because we're gonna work through this and hopefully it will make sense. That's the plan. So um, so we need to put this thing together, right? We need to plug this into that, and so we can do that. We could say, okay, well, vector f equals, for the x coordinate, 4 times sine of u, right? Because 2 times 2, 4, and then replace x with sine of u times sine of cosine of v. So say, okay, well, 4 times sine of u times cosine of v, and then for the y coordinate, it's like, we're doing a 3y times 2 times sine of u times sine of v. And, when we do that, it's going to be 6 sine of u times sine of v. And, well, finally, we'll do our z component, and it's like 2 times 4 is 8 times cosine of u. So for the z component, it's going to be 8 cosine of u. Um, and so yeah. Now we have to dot this thing. We have to dot this thing with this thing. And so the integral setup is going to be the one on the right side of this. Thus, I'm going to say, the double integral to calculate the region R, well, the integrand is going to be the dot product of this thing with this thing up here. And that's going to be dA. So now I got to dot these things together. So let's see how that's going to go. Something like that, I think. Bro, I feel like it's like Mario and like I just fell in the lava. Dude, this is not supposed to be that. Oh God, I took it wrong. How did I take it wrong? What did I do? The vector coordinates are wrong. I messed something up, but I don't think I did it in like some way that's like unsalvageable. The issue is with the cross product. Um, I didn't distribute this because it would have been minus that, making this a positive, right? Oh, okay. Right, so this is gonna be positive 4 sine squared of u times sine of v. But then what does that mean for this? Well, for this, that means that this is also gonna be positive. Um, this is also gonna be positive, right? So then when you dot it, uh, let me see here. This is supposed to be dotted with a positive. So, you know, so yeah. Um, 16 times sine of what? That's the positive 4 going with the 6, so it should be plus 24 sine of that. I reckon that I have to put in some bounds of integration for this double integral. And so I will. And I'm also gonna remove this R and this dA because we're gonna get into the meat of this here in a second. Now, so I'm gonna try to explain this the best that I can. First, I'm gonna write it in and then let me explain. So, so it's gonna be the integral from the first one is gonna be from 0 to pi, and then the second one is going to be from 0 to 2 pi. And with that, the one from 0 to 2 pi was going to be evaluated first. And 0 to 2 pi is going to be dv, and 0 to pi is going to be du. And when I looked at this, I was very confused because I'm like, why isn't it a full revolution? Why is it only pi? And the reason that u goes from 0 to pi, half of a circle, instead of 0 to 2 pi, comes down to how spherical coordinate systems sweep out a 3D volume. So let's see here. If I have a sphere, let me orient it on our axes here. Right, if I have a sphere, we can even introduce some colors, right? Why not? Um, well, the azimuthal angle, which is from 0 to 2 from 0 to 2 pi, spins completely around the z-axis. That is, it covers the whole 360 degrees or 2 pi radians. But the polar angle, it's u, and it goes from 0 to pi, and it measures the angle down from the positive z-axis. So we're going from the very top here. We're going from the very top here. Uh, we can say that this is the North Pole, and we're dropping it down to the South Pole. Okay? So the thing is it's like, we're going from the North Pole, which is u equals 0, to the South Pole, which is 180 degrees, or u equals pi. Then here is the equator. So really what we're doing is we're dropping an angle down from for so the polar angle is you're dropping an angle down from u equals 0, the positive z-axis, down to pi over 2 radians. Then you drop it down to the South Pole. So if this is the North Pole, and then this is the South Pole, and this is the equator, then you just need a 180-degree sweep. You only need u to equal pi. And the reason is because this angle here, the the um the polar angle, we're only going from the North Pole to the South Pole, right? It's not responsible for a full rotation. The azimuthal angle is responsible for a full rotation. If you let u go all the way down to 2 pi, you would sweep past the North Pole, and you would go back up to the z-axis. And now you would just duplicate the entire sphere a second time, right? Because the angle v, the azimuthal angle, 0 to 2, that's responsible for handling the full rotation around the z-axis that spins in the horizontal xy plane, right? It's like spinning a globe on the stand. Like if you have a globe on the stand and you spin it, that's the azimuthal angle. But the stand itself, that goes again from the North Pole to the equator to the South Pole, that goes from 0 to pi over 2 to pi. That's the polar angle, and if you were to do a full revolution, you're just going to duplicate it because it's just a coordinate. It's just a directional piece um to show where we are trying to place a particle or trying to show whatever it is that we're trying to show. It's like um I don't think I have to keep trying to justify it, but it's like it's only responsible for a 0 to 180-degree placement. It's only responsible for a 0 to pi placement. Um, Going past that would just duplicate it because the angle that's actually responsible for the orientation that goes past it is the azimuthal angle. So um, that's my justification as to why there is a 0 to pi to a 0 to 2 pi in this setup. I'm going to take this here, what we have at the bottom, and I'm going to move this over here. And I'm going to do two things. I am going to apply, um, I'm going to apply an identity to cosine squared of v, and I'm also going to apply an identity to sine squared of v. And I'm also going to apply the constant, no, yes, wait, yeah, the constant multiple rule and the linearity rule, and like we're just gonna do this in one sweep. So the main focus, I feel like, um, the main focus right now, it's gonna be the identity. Uh, so the first one that we'll do is gonna be cosine squared of x equaling 1 plus cosine of 2x, and then this is gonna be over 2. Then for sine squared of x equals, that's going to be 1 minus cosine of 2x. And then, like we talked about, I'm going to apply the linearity rule and the constant multiple rule. Okay, so we have 16 times the integral from 0 to pi times the integral from 0 to 2 pi times sine cubed of u times 1 plus cosine of 2v over 2 quantity integration with respect to v integration with respect to u plus 24 times the integral from 0 to pi times 0 to times the integral from 0 to 2 pi times sine cubed of u times 1 minus cosine of 2v over 2 integration with respect to v integration with respect to u plus 32 times the integral from 0 to pi times the integral from 0 to 2 pi times cosine squared of u times sine of u integration with respect to v integration with respect to u. And so let's start chipping away at this. I'm gonna factor out this 2, and it's gonna interact with this 16 in such a way as to where it's going to become 8. And then I'm gonna take the integral of this. I'm just gonna go in on this. I'm gonna go say, okay, well, sine cubed of u, that's not a dv, so, and it's a constant multiple, so that's going to get factored out for now. So we're going to set this to the side. We've already canceled out this 2, so we're going to have 1 plus cosine of 2v. When you take the derivative of cosine, it's going to become sine, but there's also going to be, there's an a, well, not an a, but there's a 2 in front of the v, so it's going to be 1/2, so that 1/2 is going to come back in. So we're going to have, let's see, sine cubed of u times, and I probably should put this in brackets because we will be evaluating this at specific bounds of integration. So it's going to be sine cubed of u times, well, this is going to be v because that 1 will become a v plus what we get when we take the derivative of sine of 2v, what we take what we get when we take the derivative of cosine of 2v, which is going to be sine, it's going to be 1/2 times sine of 2v, but I'm just going to put that sine of 2v on top. So we're going to have v plus sine of 2v over 2. And then this is going to be dv du. That's, wait a second, I just put dv, oh, wait, hold on. Wait. Evaluated from 0 to 2 pi, right? And then with the outside, it's going to have du. Plus, let's see here. We're going to dv first, so the sine cubed of u gets factored out. 24. I'm gonna factor out this 2. It's gonna interact with the 24, so we're gonna have 12 times the integral from 0 to pi times sine cubed of u, because this one is also going to be a constant multiple rule, times 1 minus cosine of 2 times 1 minus cosine of 2v over 2. That's going to be, well, I took out that 1/2. So it's going to be 1 minus, which is going to become v minus, so because cosine is going to become negative, no, just kidding. It's cosine, it, so it's going to become, cosine is going to become, well, v minus sine of 2v over 2. 0 to 2 pi as well. As for this one, it's going to be plus 32 times the definite integral from 0 to pi. You know, cosine squared of u times sine of u dv du. Cosine, so we're doing dv, so cosine squared of u just gets factored out. So it's going to be sine of u. Well, sine of u is going to become negative, right? So I feel like if that's going to become negative, it's fair to say I could factor out a negative sign. Right, so it's going to be, so it's going to be cosine squared of u times cosine of u. Oh, these guys are gonna go together. All right, whatever. We're gonna keep the ball rolling. We'll get to that. We'll get to that. It's not whatever, but we will get to that. So it's gonna go from 0 to 2 pi, and then we'll have a d on the outside. Let me just check my work. I messed something up. So the issue with what I did was I tried to integrate this sine of u when we're doing it with respect to dv. So essentially, well, that's gonna be, what we can do is, I could salvage this, but this is gonna become, man, this is gonna become, both of these guys are gonna get left alone. There's no room for us to integrate this when it's with respect to v. So this is sine of u. I'm just gonna attach a v to the end of this here, like that. Oh yeah, and because we're doing two integrals, really I should be doing like this. V equals, V equals, V equals, V equals, V equals. So now, okay, so now what happens at these bounds of integration is, like, let's just try to do this in our head because we don't have that much room, and, well, let's just try to do it in our head. So if I plug in v 2 pi for v and 0 for v, it's like, okay, 0 plus sine of 0 over 2. Well, that's going to be 0. So you're subtracting 0 from whatever you get when you do v equaling 2 pi. So it's going to be 2 pi plus sine of 2 pi over 2. Well, sine of 2 pi is 0, and so 0 divided by 2 is 0. So we're going to have 2 pi plus 0, and it's just going to be 2 pi. So, so we're going to have 8 times the definite integral from 0 to pi for what are we doing here? It's the sine cubed of u, and that's gonna be what? Sine cubed of u. Sine cubed of u times 2 pi du plus let's evaluate this at the bounds of integration. It's gonna be a similar story. Sine of 4 pi is just gonna be 0 because it's 2 revolutions. And then yeah, so we're gonna have 2 pi minus 0. So I'm pretty sure it's gonna look like this. Oh yeah, I forgot to put a du over here. And so that's gonna go like this, du minus. Oh yeah, so it's not gonna be a minus anymore. It's gonna be plus because remember how we couldn't even evaluate that at the well the variable in question was u, so we didn't even get to. I don't know why I didn't fix that. I should have fixed that. So it's actually gonna be plus 32. Um, and then evaluating this thing, it's so 2 pi. So what are we just gonna attach 2 pi to that? 2 pi. Yes, it's gonna be 2 pi. So 32 times. Just gonna go from 0 to pi. 2 pi times cosine squared of u times sine squared of u. Integration with respect to u. Oh, let's see what we can do here. I think I'm going to turn this into, I'm going to factor out the pi's from all of these things. You know, I'm looking at this thing and I'm thinking to myself, um, what's going on? And, well, let me see here. Um, I see a very similar integrand. Yeah, I see an integrand where we have sine cubed of u. And there's an integrand where there's sine cubed of u, and if I work through this and I say, okay, I'm bringing this out 16 pi of times the integral from 0 to pi, for what the integrand is going to be what? The sine cubed of u. Integration with respect to du plus um, take out that 2 pi that's in the second term here, which is going to be 24 pi times the definite integral from 0 to pi times the integrand, which is sine cubed of u integration with respect to u plus 32 times the definite integral from, just kidding, I'm gonna take out that 2 pi over here too, times the 64 pi times the definite integral from 0 to pi times cosine squared of u times sine of u, and this is gonna be, and so it's du. And right, so what we were talking about earlier was these integrands are the same. And these integrands are the same, and um this is an addition here. We're just summing these. Then I can sum what we've factored out. And then what's 16 plus 24? Well, that's going to be um 30 pi. No, 40 pi. So 16 pi plus 24 pi is going to be 40 pi. And now those integrands are the same, right? This is even in the bounds of integration. That's another important thing. The bounds of integration are also the same. which that's huge. So it's going to be 40 pi times the integral from 0 to pi times, well, not times, but a value. So we have 40 pi times the integral from 0 to pi of sine cubed of u, integration with respect to u. And and what? Well, to this we're going to add a 64 pi times the integral from 0 to pi times cosine squared of u times sine of u, integration with respect to u. Oh, let's see here. I think that this is trig sub because we have to like reduce this. Oh, this is not gonna be easy. All right, well, um, mm, yeah, well, we can go through it, right? Let's do it. We're gonna have to use an identity here for sine squared. Well, not exactly. We're gonna have to, okay, basically what I'm trying to say is this, um, this is gonna become 40 pi times the integral from 0 to pi, um, sine squared of u times sine of u. We just broke one off. Integration with respect to u. And then this second one, I don't know. This one, the second one, it's like plus 64 times pi, 64 times pi, the integral from 0 to pi times cosine squared of u. Oh no, I'm running out of room. Hold on. That's okay. See, cosine squared of u, um, times sine of u, the u, something like that. And what are we doing? We need to reduce it. We need to reduce it. So we broke it off. So what are we gonna use? A Pythagorean identity manipulation. A Pythagorean identity manipulation. I think probably this first one here. Sine squared. Sine squared. Well, we know that sine squared of x, or rather sine squared of theta plus cosine squared of theta equals 1. So if I move that cosine squared of theta to the other side, then I could say that sine squared of theta equals 1 minus cosine squared of theta. So what are we doing, guys? Well, I have to rewrite this. I gotta rewrite this. And so that's gonna be 40 pi times the integral from zero, so the integral from 0 to pi times, I'm gonna switch this out as 1 minus cosine squared of u, and then I'm gonna multiply this times sine of u. Integration with respect to u plus 64 pi times the integral from 0 to pi um, times sine of u times cosine squared of u. I'm just moving that around. Um, yeah, I don't know. I guess it's just because I want the degree in um, ascending order, descending, ascending. I digress. So let me just let's just look at this here and let's just try to see what's going on. This is going to be a u substitution, but we can't use u because we can't use u for we already have used u. So with that said, instead of u substitution, we're going to do um, lambda substitution. So if I set lambda equal to cosine of u, then the derivative of lambda equals negative sine of u du, but the issue is we don't have a negative sine of u. We have sine of u, but we don't have negative sine of u. So that's okay. That's all right, because we are going to just take this d lambda and we're going to divide it by negative sine of u. Um, so then on this side, we're just going to have du. Now that is looking pretty good, but it's a definite integral. Therefore, we have to evaluate this thing at its bounds of integration. Can I get this? There we go. And so we'll have to look at the upper bound, which is pi, and we'll have to plug it into what we set lambda to be equal to, which is cosine. But instead of u, we're going to stick in pi because that's the upper bound. So it's going to be cosine of pi, and cosine of pi, I believe, is -1, I think. And then as for the lower bounds, well, the lower bound is 0, and cosine of 0 is just 1. So, wait, no, what am I saying? Yeah, no, I'm right. Cosine of 0, but I put in a cosine of 1. Cosine of 0 equals 1. There you go. All right. And so that should do it for that. Now, before we start plugging things in, we should well, we can do substitution, but we can't use u because u's taken. So, I don't know, c substitution? Ah, yes. Everyone's favorite, c substitution. Um because everyone knows what that is, right? Uh, Everyone usually uses u or some other variable or some English letter. I don't know. Anyway, so let's set c equal to cosine of u as well. Then the derivative deep c equals um, negative sine of u. It's a situation where we don't have negative sine of u, but we do have sine of u. But we'll just take this deep c and then we'll divide it by negative sine of u. And then we'll have, oh yeah, this is supposed to have a du here. And then over here, we're just going to have a du. Then we'll have to evaluate this at its upper bound in a similar fashion to where we did previously. So the upper bound here is also pi, or yeah, but so this is gonna be cosine of pi. Cosine of pi equals -1, and then the lower bound. Oh, that lower bound, which is 0. Well, this is gonna be cosine of 0, and that's gonna equal 1. Okay. So, shall we? Um, let's see. This is gonna be 40 pi times the integral from 0 to pi. And let's put that sign first. Let's put the sign of u first, times 1 minus cosine of u, but cosine of u is set to lambda. And if it's set to lambda, that means that we have to put lambda in and square it. There we are. That's 1 minus lambda squared quantity. And instead of du, we're going to put d theta, but we couldn't get d theta by itself. D, so we got, excuse me, we couldn't get d lambda by itself. So we're going to have to put on the end here, so it's going to be 1 minus lambda squared times du, but du turns into d lambda over negative sine of u. I'm going to make it parenthetical. Well, actually, it's fine. It's fine. I'm leaving it like that. So now we'll do plus 64 pi times the integral from 0 to pi times sine of u times cosine of u. So what is that? Sine of u gets left alone, but instead of cosine of u, we're going to do psi squared because u sub. Well, psi sub. And then we couldn't get du by itself, so we're going to have times d psi over negative sine of u. All right. And well, we're gonna have some cancellations. We're gonna have some cancellations like this, and we're gonna have some cancellations like that. Um, and so we're gonna grab this and we're gonna carry this over into our next workspace because we are out of room, but it's okay because we could just grab some more. All right. Um, so now we're gonna rewrite this. We're gonna rewrite this. It's gonna be negative 40 pi times the integral from 0. Oh no, I just realized something. So, I forgot to change the bounds of integration, right? Because we didn't account for the new upper bound and the new lower bound. So, with that said, all we really have to do is just switch out these bounds as well. So here and here. And well, the new upper bound is -1. The new lower bound is 1. The new upper bound here is the same thing, -1. New lower bound is 1. Apply that over here. Because this is actually really important. This makes all the difference. We would have gotten the wrong answer if we didn't do this. Very important. Okay, so that's gonna be 40 times pi times the integral from 1 to -1 for see here, 1 minus lambda squared times negative d lambda plus 64 times pi times the definite integral from 1 to negative 1 times, uh, let's see, c squared times negative deep C. Now, there is a standard property with integral calculus that is true when it comes into factoring out negatives, um, and flipping the bounds of integration. So I'll write that out here. If we have an integral, a negative integral from a to b of some function f, right? F of x, integration with respect to x. That's the same thing as having having that same negative sign within the equation. So that's the definite integral from a to b of f of x times negative dx, right? And then that's also the same thing as just like outwardly flipping the bounds of integration. That's now we have integral from b to a of f of x dx. We are going to apply that here. So I'm going to flip those bounds of integration because I want to get that negative out of there. So this is going to be 40 pi times the integral from negative 1 to 1 for negative 1, no, excuse me, so this is going to be 40 pi times the integral from negative 1 to 1 of 1 minus lambda squared d lambda plus 64 pi from negative 1 to 1 for c squared deep C. Ah, yes. Now, what to do, what to do. Really, the power rule. So we're gonna have, oh, we will have to actually really evaluate these. Hold on, I'm gonna have to utilize more room though, because we're gonna have to really evaluate these via the fundamental theorem of calculus part 2, because it's not 0 anymore. So it's gonna be 40 times pi times lambda minus lambda over lambda raised to the third power over 3, evaluated from negative 1 to 1 plus 64 pi times c raised to the third power over 3, evaluated from negative 1 to 1. And well, here we're actually gonna have to evaluate these. So I mean, I say that because you don't have to do much when this is 0, but it's not a 0. Um, but that's okay because we're just gonna do 40 times pi. Oh, um, what are we doing here? Let's see. The first upper bound. 1 minus 1/3. 1 minus 1/3 minus negative 1 minus, I guess plus in this case now, plus 1 over 3. And then what we are going to do is do plus 64 pi times 1/3 minus plus 1/3. So what's going to happen here? I'm going to do these in forms of 1. Here we go. 40 pi times 3/3 minus 1/3 minus negative 3/3 plus 1/3 plus 64 pi of times 64 pi times 2/3. This is going to become 2/3. This is going to become plus 2/3, I think. So then it's going to be like, okay, 40 pi times 4/3 plus 64 pi times 2/3. 4 times 4 is 16 with a 0. So what is this? 160 pi over, well, it's going to be 16. We're going to do it. So 40 times 4 is 160. 160 pi over 3. I don't even know if these are divisible by one another. But it shouldn't matter because we're going to end up adding these together anyway. What's 64 times 2? 64 times 2, 128 pi, I think. Over 3. And, well, that's going to equal 288 divided by 3, and 288 pi divided by 3 is 96 pi. And so that's going to be our answer. That'll be our answer for that one. So, where did we start here? Where did we start? Over here. So, we did utilize this chart though. So, we utilize this chart, and that would be 1, 2, 3, 4, 5, and our answer is 96 pi. We found the answer to be 96, and that was the left side of the divergence theorem. So we just applied the left side of the divergence theorem to this problem, and we calculated the answer to be 96 pi. So we used the left side of this, right? But now we have to apply the theorem to the right side. Like we have to find the answer this way, because the question says to verify that both integrals in the divergence theorem for f equaling 2 times x, 3 times y, and 4 times z respectively. So we just did it this way where we dot them in the integrand, and now we're going to have to do it this way where we find the divergence of vector f. Now, one thing to note here is that, okay, one thing to note here is that there's another way that we can write this triple integral. And that's like this. perhaps now it's a little bit more clear what we are going to do, as we are going to dot it with the gradient. So this is going to be the triple integral d, and it's going to be the del operator, which is just going to hold our partial derivatives, del dot vector f dv, and that's going to be a triple integral here. Triple integral to find d. Now we're going to dot the vector, which, remember, the vector was, maybe I'll write it over here. This vector f was 2x, 3y, and 4z. So we're going to dot this thing. We're going to take the del operator, which is our partial derivatives, partial with respect to x, partial with respect to y, partial with respect to z, and we're just going to dot this thing. Um, so we're going to hit it with the dot product, and we're going to dot it with vector f, 2x, 3y, and 4z. So now this is going to be a triple integral here. D of the dot product. So to take the dot product, we're going to multiply these together, the components together, and then add them. So in other words, we're going to do the partial derivative with respect to x, and they'll line that up with 2x, plus the partial derivative with respect to y, and we're going to line that up with 3y. Then we're gonna to that we're gonna add the partial derivative with respect to z, and we're gonna line that up with 4z. And then what are we gonna have with this? Integration with respect to v, the volume. Well, if we take the partial derivatives of each of these, so here it's gonna be a triple integral, and it's gonna be 2 plus 3 plus 4 dv, that's going to be 9, and then we're going to be able to factor that 9 out. So um, 9 gets factored out from the triple integral, and then it's going to be, let's see, we want to find the volume. So that's 9 triple integral dv. So we want the volume of d. In order to calculate the volume of a sphere, it goes like this. The sphere equals v equaling 4 over 3 times pi of r squared, right? So that's going to be the formula that we're going to use. Now, that said, if we go back and we look at our problem here, we see that we're dealing with a radius of 2. So if we're dealing with a radius of 2, that means that to find the volume of this thing, it's going to be v equals 4 over 3 pi times 2, because that's our radius, raised to the third power, and that's going to equal 32 pi over 3. So remember that when you have a triple integral, right, and there's a 1 in this integrand here, that's a volume. This triple integral, and there's a 1 in the integral dv, that's a volume. So really what we're going to have is we're going to have 9 equal, it's going to be, this equals 9 times 32 over pi. Excuse me, this equals 9 times 32 pi over 3. And let's see here. 9 times 32 equals 288 pi over 3. And that equals 96 pi, which if you look back to what we just did, you'll notice that these are the exact same answers. And therefore, we've just verified both integrals for this problem in the divergence theorem. So okay. So you'll notice that 96 pi is the same thing that we got over here when we did it the first way. Therefore, we've just verified both integrals for the divergence theorem per request by this prompt. So again, they both give 96 pi, and that means that either form of the divergence theorem gives us the same answer. So we verified it. Good. All right. All right, now this problem says to compute the net outward flux for vector f equaling x, 2y, and z, where S is the boundary of the tetrahedron in the first octant formed by the plane x plus y plus z equals 1. And here I have written out the divergence theorem, and here I had drew a picture of a tetrahedron. I drew a picture of a tetrahedron. And one thing to note is that, well, this is a triangular base. The bottom of this thing is a triangle. And so if you unfolded this thing, it would look like this. Like like Sierpinski's triangle. Only Sierpinski's triangle has this, and well, this as well, and this too, and well, it even has this, and it also has this, and then it goes on forever. But anyway, this is not. Ooh, ooh, ooh. This is not Sierpinski's triangle. This is a tetrahedron. I just wanted to show what it looked like if you unfolded it. Now, um, let's just try to jump right into this. So for this here, I'm going to use the triple integral to calculate this one. Right, I'm going to use the divergence theorem. I'm going to use the right side of the divergence theorem here. So del dot vector f, this here is the divergence. This is the divergence of f, which is why over here we saw that it says divergence of f and not del dot f. It's the same thing. So I want del dot f. Well, del dot f, it's, we're taking the dot product. We're taking the dot product of these partial derivatives. So, this is going to be partial derivative of x, partial derivative of y, partial derivative of z, and I'm dotting this with vector f, which is given to us here. So this is getting dotted with x, 2y, and z. And so, well, that's the same thing as partial derivative of x with respect to x plus the partial derivative of y with respect to 2y, or I guess I should say this is the same thing as the partial derivative of x with respect to x is the partial derivative of 2y with respect to y plus the partial derivative of z with respect to z. So that's what we're dealing with here. And if we take the partial derivative of x with respect to x, it's going to be 1, plus if you take the partial derivative of 2y with respect to y, it's going to be 2, plus if you take the partial derivative of z with respect to z, it's going to be 1. And so this is going to equal 4. Um, I got the triple integral here. I want 4 dv. And I can factor the 4 out, and then I need to come up with the bounds of this thing. So I factor out that 4. You know, I don't know what the area of a tetrahedron is off of the top of my head. So I'm going to work with this. I'm going to work with this. I'm going to work this integral out the long way because I don't know the shortcut. The last problem, we knew the volume of a sphere is 4 over 3 times pi times r raised to the third power. Like we know what that is, but we don't know what the area of it, we don't know how to calculate the volume of a tetrahedron. I don't know what that is. So I take my plane x plus y plus z equals 1. And I figure out what that looks like in the x and y plane. So if I want to figure out what this looks like in the x and y plane, I set z equal to 0. So I grab my plane and I do x plus y plus 0 equals 1. And then I find out what y is. Y equals 1 minus x. Y equals 1 minus x. Let's look at this graphically. We want to look at this in the xy plane. So we're going to grab our y-axis, we're going to grab our x-axis. All right, and I'm going to graph this line, y equals 1 minus x. And as it turns out, this line, it's going to look something of the sort, something like that. And I got 1 here, and I got 1 here. This is equals y equals 1 minus x. So I can set up the triple integral as I know that z goes from the first octant. That's what that's given to me. It tells me that. So I could set up the triple integral, um, and that's where z is 0, right? In the first octant, I guess, so I'm trying to say, we can set up the triple integral because we know that z goes from the first octant. So that's where z is 0 all the way up to the plane x plus y plus z equaling 1, which is the top of my surface. So if I solve that for z, and then I get, and then I get, if I have x plus y plus z equals 1, which is the top of my surface. And if I solve that for z, well, I'm going to get z equals 1 minus x minus y. And so that's z's upper bound. I draw my region R so I can see that y varies from 0, which is the lower bound, um, up to my red line, which is y equals 1 minus x. So 1 minus x is y's upper bound, and then it goes from 0 to 1 for the x-axis here. So all I have to do is just look at the interval. So well, I guess what I'm trying to say is you could set up the integral like this. Factoring out that 4, right? So we're going from this here down to here. 4 times the triple integral. So how do I want to do this? Probably in alphabetical order, right? This is x, the interval from 0 to 1. So we're going from 0 to 1. And then y, which is right here. This is going from 0 to this red line here. And that's going to go, so our integral is going to go from 0 to 1 minus x. And then for uh for the z integral, well, we solved this plane for z, and we know that it's going to um the lower bound is going to be 0, and then our z is going to be 1 minus x minus y. If I just did x, y, z, that means that I'm going to be doing integration with respect to z, integration with respect to y, and integration with respect to x. So I'm going to grab this and I'm going to move this over here because this is my triple integral setup, and I'm going to start solving this. So I got that 4 factored out. It's 4 times the integral from 0 to 1 because that's y. I mean, that's because that's x. Then for y, it's going to be from 0 to the red line, which is 1 minus x. And then if I solve this thing for z, and there's a 1 inside of here, then I'm going to have z, but it's going to specifically be evaluated at its own bounds, namely the bound z equals 0, which is the lower bound of integration, and then z equals 1 minus x minus y, which is the upper bound of integration. And since we took care of that, then we're just going to have dy dx. Well, this thing is going to turn into, well, 4 times the definite integral from 0 to 1 times the definite integral from 0 to 1 minus x. And then this is going to be, we're just going to plug in for z, and we're not even going to evaluate it at the lower limit because it's just going to be, look, man, it's just going to be 0. So we're going to do 1 minus x minus y. And this is going to be integration with respect to y, integration with respect to x. So now I'm going to do 4 times the definite integral from 0 to 1. And then inside of here, the integrand, I'm going to treat 1 as a constant, I'm going to treat x as a constant, and I'm going to evaluate this integral with respect to y. So we're going to have y minus x times y minus a power rule situation, which is y squared over 2. And then it's going to be evaluated at its limits of integration, namely y equals 0 at the lower limit, and then y equals 1 minus x at the upper limit. And then, well, this whole thing, it's going to be um, integration with respect to x. So I'm going to evaluate this thing at its limits of integration. I'm going to say 4 times the definite integral from 0 to 1 times y minus xy times, excuse me, y minus xy minus x, excuse me, one more time. Y minus x times y minus y squared over 2. And I'm going to plug that in. I'm just going to say, and I'm not going to do the 0 because it's 0. 1 minus x minus x times 1 minus x quantity minus 1 minus x quantity squared over 2. Right now, we have 4 times the integral from 0 to 1 of 1 minus x quantity minus x times 1 minus x quantity minus 1 minus x quantity squared over 2 integration with respect to x. This 1 minus x squared here, this is the same thing as a minus b squared, only here a equals 1 and b equals x. Also, this negative x gets distributed to this binomial. So there's some changes that are going to be taking place in this integrand. This equals 4 times the integral from 0 to 1 1 minus x. I guess we could drop those parentheses for now. 1 minus x minus x, negative x times negative x is going to be plus x squared minus, I'm going to factor out that 1/2, and I'm going to apply our rule of, well, it's going to be 1 squared plus, no, just kidding, minus 1 squared minus 2 times 1 times x plus x squared integration with respect to x. This is going to equal 4 times the definite integral from 0 to 1 of 1 minus 2x plus x squared. This is going to be minus 1/2 okay, minus 1/2 times 1 minus 2x plus x squared integration with respect to x. And I'm going to grab this negative 1/2 and I'm going to apply it to each of these in this trinomial, in this quadratic. This equals 4 times the definite integral from 0 to 1 of 1 minus 2x plus x squared minus 1/2 plus 2x over 2 minus 1/2 x squared integration with respect to x. Now, what I'm going to do is I'm going to say, okay, well, this is going to be 4 times the definite integral from 0 to 1 of, well, I'm going to combine some like terms here. So 1 minus 1/2 is going to be 1/2. Then this negative 2x is going to get added with this x here. So we'll have minus x. Then this x squared, I think this here is going to be 1/2 x squared. Okay, now let me just check my work. All right, looks good. So now, well, what are we doing here? 4 times integral from 0 to 1 of 1/2 integration with respect to x minus the integral from 0 to 1 times, or yeah, integration with respect to x, plus integral from 0 to 1 of 1/2 x squared. Honestly, I probably could have just factored that out. Well, it's okay. You know what? We're gonna keep it going. Oops. Integration with respect to x. Okay. What is this? This will be 4 times 1/2 x minus x squared raised to the second power over 2 plus 1/2 times x cubed raised to the third power. Well, x cubed is raised to the third power times x cubed over 3. And then this whole thing gets evaluated from 0 to 1. Then what are we doing? Well, I think it's going to be 4 times 1/2 times x minus 1/2 times x squared plus 1/6 times x raised to the third, evaluated from 0 to 1. So now what we're going to do is we're going to have 4 times 1 over 2 minus 1 over 2 plus 1/6, which means that we're going to have 4 times 1/6. That's going to be 4 over 6, also known as 2/3. And so 2/3 will be our answer. So the flux through the surface is 2/3, and it's positive 2/3. It's a positive 2/3. So if it says it's a positive 2/3, that means that the flux is moving outwards through the surface.